Hello everyone, I am Himanshu Mishra and welcome to week 12 tutorial. In this tutorial, we are going to solve problems from 3D kinematics. Until now, we have solved many kinematics and kinetics problems, which mostly belong to 2D, and few of those problems we have also looked in 3D. In this tutorial, we are going to use the concept that we have already discussed, but in a higher dimensional system, that is in 3D. So you can see that you will see that most of the expression, most of the concept or equation that we will use today, we have already discussed in the previous classes. So some of these concepts are belongs to the very general kinematics equation and also from the relative motion concept that we have discussed previously. And we will further extend this concept to the higher dimensional system. And then this is basically a last class for this NPTEL, and but I'm going to take one additional class next week, same time, and in that class I will try to discuss all the question from the engineering mechanics course. That is, I will discuss the question from statics as well as the dynamics in a single class. So I will basically start with the equilibrium and the force and movement concept in a rigid body which is not moving, and then I will try to cover up the whole static part and then move to the dynamic part where I will discuss few problems related to kinetics and kinematics. So it's basically solving a diverse set of question in a single class. So until now, for each topic we took nearly one class, or sometimes we also took two classes. But in the final additional class, I will try to solve all the concept question from all the core concept in a single class. So in this class, we will begin with a very basic revision that you might have revision of those concepts that you might have seen in the NPTEL class in the week 12. So we will do a very basic revision, and then we will move to solving problems. So here first we will start discussing about the rotation. So you might have seen in the NPTEL class that the rotation Euler theorem states that basically we talk about the general rotation of a three dimension of a body which is placed in a three-dimensional Cartesian coordinate. Then you can actually rotate that body in various ways. You can rotate first its x-axis or y-axis, or you can choose to rotate first with y-axis and then z-axis and so on. So there are multiple ways that you can rotate the body, and these rotations are not vectors. So for example, let's say this is my Cartesian coordinate and there is one body which I am placing here. Okay, let's say this is one of my shaded part just for identification of the rotation, right? Now let's say this is my case 1 and I am rotating the body about the z-axis to 90 degree. So what will happen? This face will turn to this part, right? This will be the next part. So now this shaded part will now exist here after rotation. Then you rotate this body along y-axis to 90 degree, and you can see that this shaded part which is here, it's moved to the upper, this part. So you will get the box having the shaded part here, right? It's easy to visualize. So basically what we have done, first we exhibit theta 1 rotation along the z axis, then we exhibit theta 2 rotation along the y axis. Now if you uh, let's say this is my case 2. Now if you exhibit theta 2 rotation first, or you exhibit this second case first followed by case 1, you can write theta 2 plus theta 1, but the end result will be different, so you will not get this end result. So this is the end result for this case which I am shown in this square bracket, right? So let's do that. So let's perform first theta 2 rotation and then theta 1 rotation. So let's say this is my shaded part and I am doing theta 2 rotation. So what will happen if you rotate in this direction? So this plane, this dash part will remain as it is, right? Because you are actually rotating along y axis. So this plane remain as it is. Now if you perform the rotation about z axis, then this shaded plane will go this, rotate in this direction, right? So this shaded plane, so this is your cubic now after performing the operation. So that this shaded plane now move to this part, right? And you can see in the second case, this is your shaded plane, this back side of this cube, this. So you can see the end result for both of the case, which I have shown in the black box and in the red box, are different, which means they are not follow the commutative rule, which is the rule a vector should follow. And therefore this rotation of this system does not exhibit the vector property of the vector. But then how to actually analyze this rotation, because we often write the equation of motion in the vector form or in the scalar form or in the vector form, and in the three-dimensional case the usual step to write down the equation or to begin solving the problem is to write the equation in a vector form. So how to analyze this rotation? So it is given that if in a three-dimensional object or in a 3D system, if rotation are infinitely small, such rotation can be described as a vector quantity and follows the additive rule. So this is another rule that vector need to follow. So if you define the rotation of any system in an infinitely small quantity, for example, let's say this is my theta, which I am measuring from certain axis x. Now if I define the rotation of a very small quantity by d theta, and I define this small rotation of this small quantity in different axes for with respect to y and with respect to z, then I can actually define d theta as a vector. So now if I can define d theta as a vector, I can use all other vector formulation and I can write the equation for the rotation to calculate or to analyze the rotation rate. So this actually follow the vector property. For example, let's say I have a body and let's say this is point O. This is exhibit one of the rotation d theta, and it also exhibit rotation d theta 2. And there is a point P. So what happens each time you exhibit any rotation d theta 1 or d theta 2, this point P moves. So if you exhibit the rotation along d theta 1, the point P moves by d theta 1 cross r. Okay, this is the distance r. Then you exhibit a rotation d along d theta 2 and the point P will move d theta 2 cross r. Right? So first you exhibit rotation along d theta 1 and then you exhibit rotation along d theta 2, and the point P will move following this equation and it will reach to different point P dash. Right? Now you do the opposite thing. You consider case 2 where you first rotate this body along d theta 2 and then d theta 1. Then how the point P, location of point P will change. So it will be d theta 2 cross r plus d theta 1 cross r, and it will move to new point P dash. And you can see that in both the cases it will move to a same point P dash following the same equation, which means this small rotation of this small element is actually or can be treated as a vector quantity, and it follows this additive property. You can actually add the rotation from various uh, element together, because this is what vector do. Vector is can actually follows the linear combination of other vectors. For example, if there is a vector, it can be defined by r1 plus r2 plus and so on. So it actually follows the additive property, and you can see that from here it satisfies the additive property. And if you reverse the case, it actually moved to a same point. So this quantity which actually denote the rotation of a small element is a vector quantity. So to describe the rotation in a 3D or even in the lower dimensional system, when you define the rotation of a system or a point by a small element, you can actually write the uh, rotation in a vector form or in a vector equation to analyze that rotational motion. So now we are going to look some expression that we will or some concept that we will use to solve the problems. So most of this concept that we have already discussed in the previous class, and it's the same expression that we are going to use, but we will write this expression in a vector form. So in the previous class, in most of the occasion, we have actually write down or solve the problems by writing down the equation in the scalar form or even sometimes in the vector form. because in the scalar form it is quite easy to solve the problem, even though sometimes the mathematics become quite involved, but it is very easy to solve the problem. But nevertheless, in 3D system or in a higher dimensional system, it is preferable to write the equation in a vector form. Otherwise, the equation, if you write the equation in a scalar form, it will become too lengthy, and it will be very, the mathematics will be very much involved to solve the equation. So we know that the angular velocity can be given by theta dot. So both are the vector quantity, right? And the velocity can be defined as omega cross r, right? Now let's say this body is actually moving with some d theta. Then what should be some angular velocity? So omega equal to d theta dot. So this d theta will be omega. The omega direction of omega is along this axis. So line which specify the direction of omega and is collinear to d theta line is the instantaneous axis of rotation. So this line is the instantaneous axis of rotation. Line which specify the direction of omega and collinear with d theta is known as instantaneous axis. So omega can be defined as theta dot, whereas translation velocity v can be defined as omega cross r. Similarly, the angular acceleration can be defined as omega dot. And here, so this is my angular acceleration alpha, which actually take into account of change of magnitude plus change of direction of omega. So if omega is changing direction, even in that case you will get the non-zero angular acceleration. So even if the magnitude is fixed, so for example if your omega is 2 and it is fixed 2 rad per second, but the direction of omega is changing, that means you have a non-zero angular acceleration, even though the magnitude of this angular velocity is fixed or constant. Similarly, the translation velocity can be given by alpha cross r plus omega cross r. So this is the expression for translating acceleration. This is the expression for translating velocity. This is for the angular velocity, and this is for angular acceleration. So all this expression we have already used to solve the problem in the previous classes. And in this class, we will solve the similar problems by using this vectorial notation and in the three-dimensional system. So now let's say we have a coordinate system which is given by capital XYZ and it is fixed. And let's say there is a moving coordinate system x small xyz. So this is my fixed coordinate system, and this is moving coordinate system. Here it is k cap, j cap, I cap. And let's say there is some vector a which I am specifying. So I can actually write down, or I can specify the vector in a moving coordinate system. So it can be given as ax I cap, ay j cap, and az k cap. A is some vector, right? And I am actually specifying this vector in the moving coordinate system, blue color, which I have written in terms of small x, small y, and small z. That is, and it's in the direction of I cap, j cap, and small k cap here. Now, if I want to study the rate of change of this vector A in time, then I need to take its time derivative, right? But its time derivative should account the change of magnitude of A as well as the direction of A, right? But since I have, and also just note that this x capital X Y Z is the fixed frame, and this blue color uh, small xyz frame is the moving frame. So as this A is changing in time, the vector A is changing in time, this moving frame x small x y z, this one, it is also changing in time with some other angular velocity or some other velocity or so on. So vector A is changing and moving frame is also moving. Vector A is moving, moving frame is also moving, both are moving, and we have defined this vector with respect to the moving frame, right? So if time derivative need to account change in magnitude and direction, right? So if I take the time derivative of this vector, it should need to account the change in magnitude and change in direction both. But since I have defined this vector in the moving frame, the frame is moving, which means the frame is changing direction. So what happens? This vector is changing direction with the frame. So if this vector is changing direction with the frame, it will only account the change in magnitude. For example, let's say if I define a vector A here with respect to the initial frame, then I need to account the its change in its magnitude and change in the direction. If I take the time derivative, it will contain two parts. First, the change in magnitude and change in direction. If I define the vector A with respect to the fixed frame, but if I define the vector in the moving frame, which is all moving frame, which means that vector A is already changing the direction with the moving frame. So whenever there is a change in direction in the moving frame, vector A direction is also accordingly changing, which means the rate of change of time will be defined in change in magnitude only, right? Because this vector A is moved along with the moving frame, right? So if you are sitting on the moving frame, you will not see the change in the direction of vector A, right? Because both are moving simultaneously. So if you define the vector A in the small xyz or moving frame, this is the time derivative. But if you define the vector A in the fixed frame, then this is the time derivative, right? If you define the vector A in the moving frame small xyz, then it you can and you are yourself sitting on the moving frame, then you cannot see the change in the direction of vector A, because you and vector A both are moving simultaneously in the same fashion as your coordinate small xyz is moving. So you cannot say, okay, the vector is moving relative to me in a different direction. No, you cannot recognize that. But if you are sitting in the fixed frame, only then you can see that, okay, the vector is moving, and it is moving uh, in the same fashion as small xyz coordinate, like that. Okay, so if you take the time derivative of this equation, which I have written in the moving frame coordinate, then its time derivative only contains change in magnitude. So this is I have written in small xyz coordinate, and it will only contain change in magnitude. So this will be the equation. Now if you want to write the change vector rate of change of vector A with respect to initial frame of fixed frame of reference, then it will be A dot, it will be contain the change in magnitude plus change in direction, right? Because if you are sitting in the fixed frame of reference here, you can see the direction and magnitude both of vector A both are changing. But if you are sitting in the moving frame here, you can only see how the magnitude of vector is changing, but you cannot see the direction of vector is changing, because vector A itself written in the moving frame coordinate. So u and vector A both are in the moving frame coordinate, and you cannot see the direction of A is changing, right? Let's say this can be actually explained in the example. Let's say there is a disk and you are standing here, and your friend is sitting on a disk which is rotating, right? So your friend is just standing on a disk which is rotating. So, and you are actually standing in a fixed frame, and you can see your friend and disk both are moving, both are changing direction. Okay, both are changing direction. But if you are now if you are now stand on this disk, then you can see, and you both are not moving. Okay, you are just standing on the disk which is rotating with some angular velocity, and you can see that now you are just, your friend is stationary, you yourself and your friend both are stationary. But if you are come out of this disk and now you actually observe your friend, then you can see he's changing the direction, right? Similar concept here. So if you define the vector in the moving frame, then the rate of change of this vector in the moving frame only contain the part which is change in magnitude. If you are in the moving plane, then you cannot see the direction of vector A is changing, because the direction, sorry, because the vector A is itself in the moving plane. But if you are in the fixed frame, then you can see the direction of A and magnitude of A both are changing. So in the fixed frame, the rate of change of time is from the magnitude change as well as from the direction of change. This is what I have written here. So in the moving frame, the rate of change of vector A given in terms of magnitude change only, but in the fixed frame, the rate of change of A is from the magnitude change as well as from the direction change. So this formula now become, if you use the identity like I dot equals omega cross I, J dot equals omega cross J, and so on. Omega is the angular velocity of the frame of reference x small x y z. If you use this formula here, then you will have rate of change of vector A equals rate of change of vector A in moving frame plus omega cross A. I'm using this. So this will be your equation. So this is with respect to fixed frame and this is with respect to small frame as I have given here. So let's start solving problem based on these concepts. So we will be using some primary concept to solve the problem, like the expression of linear translational velocity, expression of translational acceleration, and we will use expression of the angular velocity as well as the angular acceleration, and also we will use this expression to define the change of any vector in the fixed frame with respect to the moving frame. So let's move to the first problem here. So in this problem we have given, at a given instant the satellite dish has an angular motion omega 1 6 rad per second and omega dot equals 3 rad per second about the z axis. At this same instant theta equals 25, the angular motion about x-axis is omega 2 rad per second and omega dot to 1.5 rad per second. Determine the velocity and acceleration of a signal horn A at this instant. So first let's before solving this problem, let's talk about some another concept here that we will use in the problem. So let's say here we have given this system. Let's say this is z axis, this is x and this is y. Let's say this z axis is moving, rotating with some angular velocity omega p, and this is a disk with point p, and it is actually rotating with omega velocity omega s. Then the resultant angular velocity of the disk, provided that it is actually appreciating with omega p, will be omega equals omega s plus omega p. So this is a resultant angular velocity of disk, right? So if this omega p will be 0, let's say z axis is not rotating at all, you will get the angular velocity of disk is omega s, which is just this. So if in this case the only angular motion is omega s, which is the angular velocity of this disk. But if there is another angular velocity at z axis, or the z component of the angular velocity you have given, then the resultant angular velocity will not be omega s. Resultant angular velocity of this disk will just not be omega s, it is omega s plus omega p. And if you take the time derivative of this, you will get the angular acceleration. So these are the four concepts. So this concept, this concept and some basic formula for linear and angular velocity and acceleration. So this we are going to use here. So in this question we have given a satellite dish which has angular motion omega 1 here 6 rad per second as well as angular acceleration 3 rad per second about z axis, and it has some angular motion of at x axis also. It has angular velocity and angular acceleration about x axis as well. Determine the velocity and acceleration of a signal horn A at this instant. So it's a very similar problem here that we have briefly reviewed. So it has both uh, angular motion of this like in this example that we have discussed shortly. It has both motion. First, there is an angular motion of this disk accompanied by some angular velocity of this z-axis. So here also you can see there is an angular motion of this along x-axis. Then there is an angular motion about z-axis. And we need to determine the angular, we need to determine the motion like velocity and acceleration of point A. And just like we have discussed, when we have given this z component of angular velocity, the angular velocity of the disk is not just omega s. It is actually omega s plus omega p. Right? Here also we have given this is omega p, let's say, and this is, let's say, omega s. Then the resultant velocity of a satellite, angular velocity of the satellite, it is just not omega 2. It is actually omega equals omega 1 plus omega 2, right? So it will be 2i plus 6k rad per second. So now we need to actually calculate the angular acceleration, because we will be to calculate the velocity and acceleration of point A, we will be using these formulas. So this is for acceleration we will use, and this we can use to find the velocity of point A. So you can see that we actually need the angular velocity and also angular acceleration to actually calculate V and A from this expression. So we need omega as well as alpha. So let's calculate the acceleration first. So to calculate the acceleration, we will be using this formula here. So we have just discussed, if I have any vector A, then it can be given as vector A in the moving coordinate plus omega cross vector A. So if my A is omega 2, so this is rate of change of A, then I can actually write down the equation for omega dot 2, which is one of the component of angular acceleration. So I can write this as omega dot 1 xyz, because you can see there are two different motion. First we are trying to calculate the motion of x along x, but since there is a angular motion along z also, so this is defined in the moving coordinate plus omega 1 cross omega 2. So this is omega 1 and this is omega 2 here. So I can define omega 2, or this are in the vector quantities. So what is omega dot 1? Sorry, it's 2. So what is omega dot 2? It is 1.5, which is given in the equation. Omega dot 2 is 1.5 in the ith direction, because it's along the x-axis, plus 6k cross 2I, right? So omega 1 is along z-axis, so it's 6k, and omega 2 is along x-axis, so it's 2I. So it is 1.5I, it's 12j. Because if I take the cross product between k and I, it will give me the direction j, and for the magnitude you just multiply 6 into 2, so it will become 12j. So this is omega 2 dot, which is rad per second square. Now I can calculate the component of angular acceleration along z, so it will be omega dot 1, and I can use the same formula, so I can write omega dot 1 in the xyz plus omega 1 cross omega 1. So what is omega dot 1 here? It is actually 3 rad per second, and omega 1 cross omega 1 will be 0, so omega dot 1 will be 3 rad per second square. Then the total acceleration will be omega 1 dot plus omega 2 dot. So it's same that we have discussed here. So this is the omega resultant spin of this disk, which is omega s plus omega p. If you take the time derivative of this, you will get the omega dot s plus omega dot p. Similarly, I have omega dot 1 and omega dot 2. If then the resultant will be the angular acceleration, which is 1.5. So omega 2 is 1.55 plus 12j, and this is omega 1 is 3k. So 1.5i plus 12j plus 3k rad per second square. So this is my angular acceleration. Right, so we have discussed that in order to find the velocity and acceleration, we need angular velocity and angular acceleration. So we already have angular acceleration and angular velocity now. So now we can actually calculate the velocity of point A, and we will use the same formula to find the velocity of point A. We will be using omega cross r. So velocity at point A will be omega cross RA. And now we need to define position vector RA. So this can be defined in, so the distance from O and A is 1.4, then my RA will be 1.4. Along the y-axis, what it will be, this is angle 25, so it will be cos 25 along y-axis, and 1.4 sine 25 along z-axis. So along this z-axis it's sine 25k. So this will be my position vector, right? And my omega is this 2i plus 6k. So until now we are following the concept that we have discussed now. Like here, just to recap here, if you have a disk and it is rotating with some angular velocity omega s, then the angular velocity of this disk will be just omega s. But let's say you have some another rotation motion going on along z axis, this is omega p, then this resultant rotation of this disk is not just omega s, it is not omega s, it will be omega p plus omega s in the vector form. And the same concept here we used, because there was a motion along the z axis and there was the motion along the x axis. So the rotation of the satellite is not slowly determined from this omega 2. The rotation of the satellite will be omega 1 plus omega 2. This will be my resultant rotation of the satellite. So this will be omega 1 plus omega 2 cross RA. So VA will be, so omega 1 plus omega 2, that is the resultant angular velocity is 2i plus 6k. 2i plus 6k cross product with position vector RA, which is 1.4 cos 25j plus 1.4 sine 25k. So I can split this as 2i cross 1.4 cos 25j plus 1.4 sine 25k plus 6k cross 1.4 . Right, we just follow the property of a vector. So now we can take the cross product. So this bracket quantity can be written as 1.268j plus 0.591k. So basically you are taking the cross product with this quantity. So if I take with 2i first, 2i cross with this quantity, so I into j will give me kth direction, and 2 multiply by this quantity will give me the magnitude. So it will be 2 multiplied by 1.268, 2.536, the kth direction. And if I take the cross product of this quantity with 2i, it will be pi cross k into j. It will be in the direction of j with the magnitude of 2 multiplied by 0.59, which is 1.18 j. Similarly, 6k multiplied by this one shall give you 7.59 magnitude, and k into j, will be in ith direction, and 6k into 0.591k, so it's like k into k will be 0. So this will be minus actually, because k into I will be minus. So this also will be minus. This is minus j. So this is your velocity of point A in meter per second. So you can see it's pretty much simple to use the vector notation. And in a similar manner, you can actually calculate the acceleration using this equation. So here you need angular acceleration as well as the angular velocity. So your acceleration of point A will be alpha cross RA omega cross RA. So we have already calculated alpha, which is this. So 1.5 I plus 12j plus 3k cross RA, which is 1.268j plus 0.59k plus omega cross RA. So omega was 2I plus 6k cross product with 2I plus 6k cross product with RA, which is 1.268 J plus 0.591K. So we just substituting into the formula and we will get the answer. So on calculating, you will get this as 10.4 I minus 51.6 J minus 0.463 K cap meter per second square. So this is the acceleration of point A. So here you can see that we are given the motion of a satellite. So its angular motion along z axis is given as omega 1, which is the angular velocity, and omega 1 dot, which is the component of angular acceleration, and it is also moving in the x axis with angular velocity omega 2 and component of angular acceleration omega 2 dot. And we saw that in the example here, then the resultant spin of this disk is not just omega s when you have another angular motion component of angular motion present. It's actually omega p plus omega s. This is a similar problem here. So here we have given omega 1 and omega 2. So the resultant motion of a satellite is not just omega 2, it is actually omega 1 plus omega 2. And if you take the time derivative of this, you will get the angular acceleration. So the objective here is to calculate velocity and acceleration of point A. And the velocity we all know that it is given as omega cross r in the vector form, and the expression of alpha will be alpha cross r plus omega cross r. So to calculate the velocity and acceleration, we need angular acceleration as well as angular velocity. So we calculate that. So the angular velocity, resultant angular velocity, we got as by using this formula omega 1 plus omega 2, which is given by this. Then to calculate the angular component of angular acceleration, we actually use this equation where we define the rate of change of some vector A in terms of a rate of change of vector A in x moving frame as well as the movement of this frame, which is omega. So first we consider omega 2, we use this equation to write down the equation for omega dot 2, and we got that, and using the same equation we used to calculate omega dot 1, and we found that omega dot 1 is just 3 rad per second square in the z direction. Then using omega dot 1 and omega dot 2, we calculate angular acceleration alpha. So this is when you actually take the time derivative of this expression, right? So once you get alpha and omega, you actually easily find out the translation velocity and translation acceleration, because you need angular acceleration and angular velocity to calculate these quantities. So our whole objective is to calculate the translation velocity and translation acceleration here, and to calculate that you actually need to know about alpha and omega. So omega can be given by the summation of omega 1 and omega 2 in case if you have given the component of angular velocity in the two direction, and to calculate the alpha you actually use this expression here. That's all. So just keep in mind your end goal, which is translation velocity and acceleration. What are the quantities you need to find to calculate v and a. So let's solve a similar problem again. Just a minute. So in this question, we have at a given instant, the antenna has an angular motion omega 1 3 rad per second, and omega 1 dot is 2 rad per second square about the z axis. At this same instant, theta equals 30. The angular motion about the x axis is omega 2 and omega 2 dot. Determine the velocity and acceleration of the signal horn A at this instant. The distance from O to A is d. So you can see that it's a similar problem actually, and we have given the angular motion about this x-axis, which is given by omega 2 and omega 1, and there is an angular motion about z-axis as well. So the spin of this antenna is not equal to just omega 2. Since we have also given the angular velocity at z-axis, it will be equal to omega z plus omega x. So omega z is omega 1, so it will be omega 1 plus omega 2. So this will be the resultant angular velocity of this antenna. If there is no angular velocity at the z-axis, then the resultant angular velocity is easy to visualize. It will be just omega 2. That is, this antenna is moving here like this along this x-axis. But since there is a motion along z-axis as well, then it is not just this angular velocity, it is this, which is omega 2, plus this, which is omega 1. This will be the resultant angular velocity of this antenna, and that we have discussed in the previous question as well as just before the previous question about from this simple example. So it is given that the distance of O to A is d, this d, which is 30 degree from y-axis, right? So my position vector RA. So first, to find the velocity and acceleration of signal horn A, so this is the signal horn A. It is given by omega cross RA. So you need position vector and you need angular velocity. So angular velocity, what is the resultant angular velocity of the antenna? It is given by this quantity. So resultant angular velocity is omega 1 plus omega 2. So what is omega 1? Omega 1 is 3 rad per second and it is along the z axis. So it is 3k, and omega 2 is 1.5 and it's along the x axis, so it's 1.5 I cap. Rad per second. And what is the position vector? So it is OA along the x, this is my y-axis, so along the y-axis it will be OA cos 30, and along this z-axis it will be OA sin 30. So basically we are just taking out the component, so it will be OA cos 30 j cap, OA sin 30 k cap. So RA will be 3 cos 30 j cap plus 3 sin 30 k cap. So it will be 2.6 j cap plus 1.5 k cap. Just giving in feet. So now we have RA, we also have omega. Now we can easily calculate the velocity at point A. It is omega cross R, which is omega is 3k plus 1.5 I cross 2.6 j plus 1.5 k. So first 3k cross 2.6 j, so it's 3 multiplied 2.6 k cross j. So this is my cross. So here, to avoid the confusion between multiply sign and the cross product sign, here I am writing cross product as this by this notation. So this is my cross product, which will give me 7.8 magnitude, and k cross j will be minus I. So it's minus 7.8 I. Then this and this will be 0 because it's a cross product between k and k, which is 0. Then this and this quantity. So 1.5 multiplied 2.6 I cross product with j. So I cross product with j will give me k, and the multiplication of this is 3.9, so this will give me 3.9 k. Then the cross product of 1.5 with 1.5 k. So 1.5 into 1.5 I cross k. So this will give me minus j, and this will give me 2.25. So it's minus 2.25 j. So this quantity will become minus 7.8 I plus 3.9 minus 2.25 j plus 3.9 k meter feet per second. So this is my velocity at point A. Now from this equation, if I take the time derivative of this equation, I will get the angular acceleration. Omega dot equals omega 1 dot plus omega 2 dot. So omega dot equals omega 1 dot plus omega 2 dot, and we have already given omega 1 and omega 2 dot, which is 2 and 4 respectively. So to calculate omega 1 dot, we will use the same equation that we have used previously. Previously we use this expression to calculate omega 1 dot and omega 2 dot. So the omega 2 dot will be omega 2 dot in the moving frame plus omega cross r. And to calculate the omega 1 dot, it will be omega 1 dot in the moving frame. Sorry, it is omega. It is omega cross omega 1. And this is omega 1, this is omega 2. So if you follow this relation, you will get the angular acceleration 4i plus 4.5 j plus 2k. And we have already done this exercise in the previous problem here. Right? So my acceleration will be omega dot cross r plus omega cross r. So this is my velocity va. So its acceleration at point A will be omega dot cross r plus omega cross va. So this underscore actually means that I am writing in the vector form. So this is 4I plus 4.5j plus 2k cross 2.598 j plus 0.5k plus 3k plus 1.5I cross product with the velocity we have found, which is minus 7.8 minus 2.25 j plus 3.9 k. So in just substituting all this quantity into the formula, we have got this, and now we all is left to calculate the quantities. So on calculating, we'll get A as 8.3I minus 35.2 J plus 7k feet per second square. So in this question, we have been asked to calculate the velocity and acceleration of point A here. So this antenna is actually moving with or spinning with angular velocity omega 2. So the resultant angular velocity of this antenna is not should not be omega 2, because there is another angular velocity along the z axis. So in that case, the resultant angular velocity is given by omega 1 and omega 2. So to calculate the velocity, we need this resultant angular velocity with a cross product of position vector. So once we found out the resultant angular velocity, which is omega 1 and omega 2, you can actually easily calculate the velocity of point A. But to calculate the acceleration, you need the component of angular acceleration like omega dot 1 and omega dot 2, and for that we will be using this equation where we define the rate of change of vector can be defined as rate of change of vector in the moving frame plus omega cross A. So in place of A, I can write omega dot, in place of A dot I can write omega dot 2. Then it will be omega dot 2 equals omega dot 2 in the moving frame plus omega 1 cross omega 2. So omega 1 is the velocity along the z axis, angular velocity along the z-axis because the antenna is not moving alone. It actually contains secondary motion omega 1. So it's like a moving frame. So there is one movement of this antenna due to this omega 2, then it's in the moving frame because there is another angular motion in the z-axis and this is omega 1. So from that we actually calculated the omega dot 2. Similarly, we will calculate omega dot 1 here in this expression and we found that it is just equal to omega dot 1 in the moving frame. So using this we actually get the omega dot, which is the angular acceleration. So once we get the angular acceleration, we can actually substitute that value to calculate the acceleration. So let's solve one more this type of problem and then we will move to the next concept. So here at the instant when theta equals 90, the satellite's body is rotating with an angular velocity of omega 1 and angular acceleration of omega 1 dot. Simultaneously, the solar panels rotate with an angular velocity of omega 2 and angular acceleration of omega 2 dot. Determine the velocity and acceleration of point B. So it's a similar concept problem like the two problems we have solved previously. So it has been given that the satellite is moving with the angular velocity omega 1 and then there is a solar panel which is actually moving, rotating or with the angular velocity omega 2. So the rotation of the solar panel is given by omega 2, but this is not the resultant rotation of the solar panel. It is a rotation of a solar panel, but since we have given another angular velocity of a satellite, the resultant rotation of a solar panel will be omega 1 plus omega 2. So this is what we have seen in the previous two question as well as just before the solving the problems here. So this will be the resultant rotation of this solar panel, omega 1 plus omega 2. Only the case when omega 1 is 0, which means the satellite is not rotating. Only in that case, the resultant rotation of this solar panel is given by this omega 2. But since we have given another angular motion in the z-axis, which is the angular motion of the satellite, what is happening? The satellite is rotating and at the same time the solar panel is rotating in some other direction. So two motion actually occurring at the same time. So the resultant motion of the satellite will not be this one, omega 2. It is actually omega 1 plus omega 2. So my resultant angular acceleration angular velocity will be omega 1 plus omega 2. Now in order to get the velocity and acceleration of point B, so we need to find the velocity and acceleration of this point. We have Vb equals omega cross multiplied by ROB. So we need to find this and this quantity. So resultant angular velocity can be given by this one. So which is omega equal omega 1, which is given in the question 6 in the y plus 15k. Now we need to determine the angular acceleration. So we take the time derivative of this. So we will get omega 1 dot plus omega 2 dot. Now let's say if my xyz is a moving frame, then I can actually define the rate of change of vector as rate of change of this vector in the moving frame plus rotation of this moving frame with respect to some same vector A. All this in the vector quantity. Right? So if my A dot is omega dot 2, then following this equation, my omega dot 2 will be omega dot 2 in the moving frame plus, then this will be the rotation of moving frame. So here, if my satellite is having omega 2 and it is in moving frame, this moving frame is the rotation of the satellite, right? And it is actually moving with omega 1. So my capital omega here is omega 1, this. So omega 1 cross omega 2. All this in the vector quantity. So my omega 2 in the, so this is omega dot 2 in the fixed frame. And my omega dot 2, which is given in the question, is 1.5 rad per second square. So this will be 15 multiply 6, so it will be 90, and k cross j will give me minus I. So it will be minus 90I plus 1.5 j rad per second square. So this is my omega dot 2 with respect to the fixed frame. And using the similar formula, we actually calculate omega 1 dot. So this is 0, so omega 1 dot is just omega 1 dot with respect to the moving frame, and it is given in the question as 3 rad per second. It's given in the question. So now we have omega 1 dot and omega 2 dot, and we can actually easily calculate the overall resultant angular acceleration by using this formula. So my omega 1 is 3k and omega 2 is this, minus 90I plus 1.5 j. So this is my angular acceleration vector. Now we have been discussing so far that to calculate the acceleration we need angular acceleration vector as well as the angular velocity. And we have calculated this angular acceleration vector here, and we know this angular velocity also. So by using this equation I can write down I can actually find the acceleration of point B. So yes, my angular acceleration that we have found is this, which is 90 minus 90I plus 1.5 j plus 3k cross product with position vector ROB. So to find the position vector here, so this is ROB and you can actually calculate the position vector from the diagram itself. So this is ROB. So it is 1 feet in the x-axis and 6 feet with respect to y-axis. So it is minus 1I plus 6j, then omega cross r, which will be given as, so this is my omega cross omega cross r. So overall we need to solve this equation, and in the vector quantity it's pretty much simple to solve. So I'm solving this. I will get 243I minus 1353j plus 1.5k. So this will be my acceleration, and the velocity can be given by this expression, which is 6j plus 15k cross product with ROB, which is minus 1I plus 6j. So on calculating this, we will get minus 90I minus 15j plus 6k. So this is my velocity. So let's move to the new concept. So now we will solve the problem where we have given the fixed frame as well as the translating or moving frame. So the velocity, so let's say there is one point B and this is point A. So here the motion of this body can be regarded as the instantaneous translation of body and rotation about the instantaneous axis passing through point A. Can be given as the translation motion plus rotation along instantaneous axis pass through A here, because this moving coordinate system x, y, z has the origin at point A and it is rotating along the axis which is passing through A, right? So in order to calculate the in order to calculate the motion of point B, first we need to figure out velocity of B with respect to A, which is omega cross RAB, and acceleration of B with respect to A, which is alpha cross R A with respect to B plus omega cross R A with respect to B. So it was a similar formula that we have used in the previous problem. Then the relative motion can be given as VB equals VA plus VBA, and AB equals AB, AA plus VB, A of B with respect to A. So in the previous problems we actually were calculating these quantities, but now there is some random point which is B, and we need to calculate the velocity and acceleration of that point. right? So in the previous problem, what we have, so all the points are actually all the points were actually located at point A, and in order to calculate the velocity and acceleration of point A, we have used these equations. But now there is one a random point which is not located at the origin of moving coordinate system. It is located at some random location B. So the velocity of B can be actually given with respect to velocity of A, but for that we need to find the relative velocity of B with respect to A. So we will use these equations to solve the problem. So it's a similar exercise, it's just we have to look for the velocity and acceleration of point A as well. So let's solve the problem here. So here the disk A rotates at a constant angular velocity 10 rad per second. If rod BC is joined to the disk and a collar by ball and socket joint, determine the velocity of collar B at the instant shown. What's the rod angular velocity omega BC if it is directed perpendicular to the axis of rod? So you can see this disk is actually rotating with some angular velocity 10, and it is actually creating the motion at point B. So just recall that we have solved plenty of this kind of problem in the previous classes, where we have a member, where we have given the system with a different types of connecting member, and if there is a motion at one member, it actually leads to a motion of another member. And if we have given the motion or the like velocity and acceleration of one member, then how to calculate the velocity and acceleration at some other point or of some other member. So for such problem we actually use the concept of the relative velocity. So we are using the same concept here, just it is given in a 3D coordinate system. That's the only difference here. So we will write the equation in the vectorial form to solve. So to determine the velocity at point B, we will have Vb equals Vc omega Bc cross Rb with respect to C, right? And this is what we have done previously when we were solving the relative velocity concept. So for a, we have given the motion of C, and we need to find the motion at B, right? So you can see that this at B, the collar actually can move in the y direction. So Vb can be equal to minus Vbj. And omega Bc will be omega xi omega yj plus omega jk. And we don't know omega x, omega y, and omega z. Right? Because we have given this omega, but this is the omega for a disk. The disk is rotating with this angular velocity. But you can visualize here, this disk is actually rotating one end of this shaft, and this shaft is rotating at this point, and it is producing a translating motion at the another point. So it has some rotation along x, y and z axis, which is given by omega x, omega y and omega z. And we don't know these quantities, omega x, omega y and omega z, and we need these quantities to calculate the velocity, the translating velocity of point B. So first let's calculate omega x, omega y and omega z. So using this equation 1, we have minus VBJ then what is the velocity of point C? Here, because we have given the angular velocity, so velocity of point C will be omega C cross this radius or diameter of this disk, right? So it will be given so this d can be given in the y-axis here, and this omega is along the z-axis. So it is like k cross j, which will give I direction, right? And the magnitude is 10 into 0.1 meter. So it is 1. So my VC vector is 1i. So it is 1i here, which is VC plus this vector omega BC cross RBC. So if I write in the matrix form, here I have omega x, omega y, omega z, and the position vector here is given by here. So this is z component, this is y component, this plus this is the y component, and this is my x component. So it's minus 0.2. So basically this RB with respect to C is minus 0.2i plus 0.6j plus 0.3k. So it's minus 0.2 here, 0.6 here and 0.3 here, right? So if you solve this matrix, you actually get three equations in terms of omega x, omega y and omega z. So just solve this matrix part only. You will get omega x 0.3 omega y minus 0.6 omega z plus omega y minus 0.2 omega z minus 0.3 omega x. So this is I direction, this is j direction plus omega k, omega x 0.6, 0.2 omega y. This is kth direction. So you can write this matrix part into I, j and k. So here you have I, j and k component, here you have I and here you have j component. So basically this vector equation which have I, j, k component, you can actually split this equation into three parts. One in completely in the I direction, one completely in j direction and one completely in k direction. So this will be 1 minus 0.3 omega y minus omega 0.6 omega z equal to 0. This is equation 1. 0.3 omega x plus 0.2 omega y equals VB. This is in j direction. 0.6 omega x 0.2 omega y equals 0. This is in z direction k. So these are the three equations, right? You can see that the three unknowns are omega x, omega y and omega z, and we have three equations, but there is additional one more unknown, VB, that we need to find. So this is our end goal, VB. So basically there are four unknowns and three equations. To solve this four unknown, we need one more equation. We need four equations. So what we do, we can actually use the vector property here. So here you can see the omega BC is having a cross product with RBC. R, this position vector, B with respect to C. So this quantity having the cross product with this quantity, and it is a non-zero, right? It is a non-zero, which means these two components are not parallel to each other, because if they are parallel to each other, then the cross product of these quantities should be zero, right? But they are not zero, which means they are not parallel to each other. They actually perpendicular to each other, right? Because if they are perpendicular, only then you can take the cross product. Otherwise, you cannot take the cross product. And if it is not zero, right? So they are not zero, non-zero quantity, which means these two quantity are perpendicular to each other. And if these quantities are perpendicular, which means if I take the dot product of these two quantity, it should be zero, right? So it's a basic vector property that I'm using, that you might have seen in the basic mathematics course, right? So if two vectors, let's say y and x, they are perpendicular, so I can actually take the cross product of it and it will be non-zero. But if y and x are parallel or along the same direction, then this will be 0 and x dot y will be 1 if they are parallel to each other. Here the x dot y will be 0 and x cross y is not equal to 0. And if they are parallel, then x cross y equal to 0 and x dot y equal to 1 if they are parallel. So if these are perpendicular, then their dot product should be 0, right? Omega BC dot R be with respect to C 0. So my omega BC is omega xi, omega yj, omega k dot with R be with respect to C, which is minus 0.2i plus 0.6j plus 0.3k equal to 0. So this is one of the trick in case you need one more equation. So I'm actually explaining one of the trick here. So because we have only 3 equation and 4 unknowns, so we need one more equation. So how to get one more equation? So one trick is to use the vector quantity. So using this trick, you can actually get fourth equation. So if you solve this, you take the dot product of this term and this term, this term and this term, and this term and this term. So you will get minus omega 2 omega x plus 0.6 omega y plus 0.3 omega z equal to 0. So this work as fourth equation. So this is our objective, to get the fourth equation. So we solve for the 4 unknowns. So and we use this trick to solve. So the purpose here is to keep looking for different method or tricks to find the fourth equation. So like in the kinematics problem or in the equilibrium problem, we used to solve for 3 unknowns by writing down 3 equations. So the one equation was for force balance in x, force balance in y, and then the moment equation. But if you have a 4 unknowns, then you should look beyond these 3 equations. So in one of the problem in one class, we actually write the equation by using kinematics, where we define the displacement with respect to velocity and acceleration. So we got 4 equation and we solved 4 unknowns. So here also we use one of the tricks, because we know that this quantity is finite, it is not zero, which means these two quantities are perpendicular to each other, and this means their dot product should be zero. So by using this property, I can write fourth equation. So if I solve equation 1, 2, 3 and equation 4 together, I will get omega x as zero point 0.2, omega y as minus zero point 0.6, omega z as 1.36, and Vb equals 0.33 meter per second. So this is our end objective, to calculate the velocity at point B. So this a bit tricky problem, because so just to recap here, we need to find the velocity of this socket at point B, and we use this relative velocity formula, because in the previous class we saw that if we have given the velocity of one point, then we can actually calculate the velocity and acceleration of another point by using this relative velocity expression. So we have given the velocity of point C here, and we need to find the velocity of point B. And we found that we have unknown omega x, omega y, and omega z when we use this equation, relative velocity equation. So we write down this three equation, and we found there were four unknowns. So we need to find another equation. So we use the vector property here to get the another equation. So in the end we got four equation and four unknowns, and that you can easily solve to get the required unknown quantities. So let's solve next problem. So here the rod assembly is supported at B by a ball and socket joint, and at A by a clevis. If the collar at B moves in the xz plane with a speed Vb, which is 5 feet per second, determine the velocity of point A and C on the rod assembly at the instant shown. So you can actually interpret which concept you have to use. You have already given the velocity of point B, and you have been asked to calculate the velocity at point A and point C, which means you need to use the relative velocity concept. So to find the velocity of point A, it is given as Vb plus Va with respect to B. So Vb, this will be omega ABC cross Ra with respect to B. So all this concept we actually already have seen in the previous classes when we were solving the relative velocity concept, and also we discussed in a very briefly manner before we solved the previous question about this concept. Right, so it's a similar problem here. So we can write this equation in terms of the matrix form. And RAB can be given as 4 feet in the y direction and 3 feet in the z direction. So it's 0. So RA with respect to B is 4j minus 3k. So it's 4 minus 3. So when you solve this way, and VB is given 5 feet per second. And you can see that it is in x and y direction. So there is one component in the x direction here and one component in the y direction. So my VB vector is 5 cos 30 I minus 5 sin 30 j. So 5 cos 30 I minus 5 sin 30 j plus this matrix quantity. So as usual that we have seen in the previous problem, we can actually write, so this is the vector equation, and we can decompose this equation into three equations, in the x direction, y direction, and in the z direction. So in the x direction it is 5 cos theta 3y 3 omega y plus 4 omega z. In the y direction it is 3 omega x equals 0. The z direction it is 4 omega x is 5 sin 30 equals minus VA. So as usual, 4 unknowns and 3 equations. So you can use the vector property again. Right? So you can see this joint y, there is a constant. So this point A can either move up and down, right? So this point A here only having translation motion. It can, so this along this point A here, it cannot rotate because there is a joint which is provided here. So it can actually move upside and downside, but it cannot move left and right. It cannot move backward and forward also. So it cannot rotate, which means my omega in the jth direction is 0. So you can see the purpose here is you have to define the fourth equation, and on what condition you are defining the fourth equation. So in the previous question we saw that omega cross r is not 0, right? So if it is not 0, which means omega and r are perpendicular to each other, which means omega dot r is 0. So we use this condition to obtain the equation. And in this problem, we need to define the fourth equation. So on what purpose we can define? So we actually saw what are the motions which it is exhibiting. So in the previous one, there was omega x, omega y, and omega z. All kinds of motion were there. But here in this question, since this is fixed, this has some constant. This point A cannot actually rotate, but it can move upside or in the downward direction, but it cannot rotate. So we can use this information. So you have to open up a little your mind to determine the condition you have given in the diagram or in the question. So here we have know from the diagram that it cannot rotate in the y direction. So it will be omega xi plus omega y j plus omega k in that jth direction is 0, which means omega y j dotted with j is 0, because if you take a dot product of j with I and k, it is anyway will be 0, doesn't matter. But so this will be the equation, and omega, this will give you omega y equals to 0, right? Omega y equal to 0. So you put this condition in the above equation. So from equation 2, omega x is also 0. So omega x equals omega y equals 0. So using the above equation, you will get omega z, which is 1.08 rad per second, and VA 2.5 feet per second. So this is our VA. Now we need to find the velocity of point C, this. So using the same formula, VC equals VB plus omega ABC cross RC with respect to B Now what is RC with respect to B? So this is 2 feet in the X, 3 feet in the Z. So RC with respect to B will be 2I minus 3K. And now we know this quantity. We have already found this component of this quantity. So now we know this quantity. So it is just formula based question now. So VB we know that it's 5 cos 30 minus 5 sin 30. And we also know this quantity. So omega is 0, omega y is 0 and omega z is 1.08. And this is RC with respect to B is 2I minus 3K. So it's 2, 0 minus 3. So when you solve this, you will directly get VC 4.33I plus 2.17 J minus 2.5K. So you can see this question has multiple component. The last part is actually straightforward. You have used this relative velocity concept to find the velocity of point C. But in the previous one, you need to again fourth equation and you use the fact that the rotation along y is constant, which means omega dot j equals 0. So you from this you get the fourth equation to solve for the unknowns. So this tutorial we actually looked the concept, two concept, one from this relative velocity and one from using the general velocity and acceleration equation. And we just briefly revised how to and where to use these kinds of equation. So in the next week, I will try to recap all the problems from the statics as well as dynamics uh, in a single tutorial lecture. I will be revising all the concept. I mean, not exactly I will revise the concept, but I will solve from all the concept, solve problem from all the concept. It will help you to clear the concept from, because in the end you are going to give the exam, and in the exam the question from all the topics will be there, so it will help to distinguish which concept you need to use, because especially in the dynamics there are so many concepts, and in most of the concept you saw that you have to use the same expression and same knowledge, and there are just a little difference. So it will actually help you to figure out which exact concept you need to use in the exam. So we will see next week.